Morning. For those who haven't put a face to a name, I'm Mike Jacobs. I'm the co-chair behind Jono. I hope you all enjoyed the reception last night. We put quite a bit of thought behind it. For those who didn't make it, I apologize that you missed out. So I'm not going to delay. I'm going to walk right into introducing Foy Shiver, who is our session chair for novel metrics.
Thanks, Michael, and good morning, everyone. I'm Foy Shiver from the APWG. First time at FloCon. I've been working with Cert and Jonathan and most of these guys for a while. Really excited to be here. I will admit that the technical level is way beyond most of the events I go to, so I'm having a constant headache, but I'm trying to keep up. But with that, I'll get us on. We've got Leigh Metcalf's going to talk to us this morning. Leigh is a PhD with mathematics from Auburn, down from my part of the world. And with that, I'll let her, she's going to talk to us a little bit about some math and clustering.
Yeah, math.
First thing in the morning.
First thing in the morning, y'all get to hear me talk about math. I know you're excited. So last year I talked about encounter complexes for clustering network flow, and this year I'm extending the idea a bit. So for those of you who are not here last year, I'm going to briefly cover it. There's more slides that I'm actually going to talk about, but that's so you can download them later and not be walk in the middle of the story. So now we have our legal. Lawyers may just say this stuff. I've never read it. So clustering network flow for fun and profit, and because I think it's a good time, I guess that's the fun. It's previously been done for finding Trojans, botnets, spoof flows, but those methods all use known behavior to find repeats of that behavior. I know what a spoof flow looks like. I'm going to cluster using that. I don't like that. I don't have a clue. The encounter complex uses no prior knowledge. It uses encounter complex traces which record when two nodes meet, like two lions meet at a watering hole, or two users use the same wireless node. That's actually how it's been studied in the past. So it looks like that. Encounter time, node 1, node 2. Well, this is network flow. We don't have an encounter time. We have an encounter time period. So I define it for network flow as maintaining the time period with a start time and the end time rather than just a moment in time, because, flows are not just a moment in time. Flows can last, what's the timeout, 1,800 seconds or something? Flows can go. So to create the complex, my encounter trace is a node in my graph. So then I put an edge between the two of them. At the end of one occurs when delta seconds of the start of the next, where delta is defined however makes you happy. Let's assume delta is 8. Here's an example of an actual encounter complex. So now I'm going to go a little fast. Sorry, I just want to make sure I get to the actual fun stuff. Well, what I consider fun stuff, sorry. For an example, I liked the LBNL data set. I like this data set for this stuff because it's not just an example of, I found this network bad thing, here's a PCAP that shows how I found the bad thing. Or the thing with dumps from events is, hey, there's a 50 gig Switzerland exercise where 99% of it goes to one of two ports. This is not a very good example for me. This is boring as far as I'm concerned. But this is collected, it actually is, normal traffic that happens in a network. And so I just chose some random time with about 47,000 network flows, a bunch of IP addresses, a little over an hour of traffic. And I created complexes for 7 values of delta. So you see, when delta is 1, I get a lot more complexes. But remember, as delta grows, it contains the graphs beforehand. They just sort of get subsumed into the larger graph and things grow. So here's my other fun thing about visualization. As anyone who's worked with me knows, I'm not too into it, because I can't actually analyze these graphs and actually tell you what's going on without actually drilling in, spending time, as opposed to running one program that does that for me. We analyze them by looking at 2 things: the vertex with the highest degree, so that's the flow that has the most in common with everybody else, and the node that is most prevalent through the graph. So here's an example. It has the most common node of 128.3.2.128, port 631. Hey, I think that could be printing. So this is an encounter complex that contains printing traffic. So now comes the fun part. I've run through encounter complexes. I hope you kept up. I'm sorry if I went too fast. But I've created these graphs from network flow. Now I want to cluster the graphs so that I have like traffic that may or may not share that node and IP, port together. I want to find similar web traffic patterns that not necessarily go to the same IP addresses. So there's similar traffic, fewer things to look at. That's a bonus. So there's 3 steps to creating the clusters. First, we look at similar port. And I know Mike Collins is going to tell me port's not the right thing I should have used. I should have also used protocol. I'm sorry, Mike, I didn't use that yet. Now, I then want to look at things with a similar amount of vertices, and there's a reason for that, aside from the fact that, well, it sounded like a good idea at the time. The reason for that actually has to do with the 3rd step, and now we are going to digress into graph theory, and I hope you had some coffee this morning, and I apologize for hitting you with some math. Graph isomorphisms, i.e. telling if 2 graphs are exactly the same, is an NP-complete problem. This really means you can't do it very easily. Graph similarity, that is, one step away from graph isomorphism. How similar are these 2 graphs? Have as many methods as mathematicians working on the problems, and I'm really not exaggerating on that. So of course I created my own method. But I created my own method because it worked for the kind of graph I'm looking at. I didn't want a generic method that solved all problems of graph similarity. So I look at the degrees of the vertices within the graphs. There's sort of a measure of similarity, okay? If I have an encounter trace, which is a large degree, it is very similar to a lot of other things within that graph. If it has a small degree, it only has a small bit of similarity. So I decided I would use degree as my basis of graph similarity. So now I take my 2 graphs, and I create a sorted degree vector for each graph. It's important that you sort them, because if you don't sort them, it's not going to work very well. So if one vector is shorter than the other, I want to pad it with zeros. So this is the reason for the previous reason of I'd only want the vertices within 10% of each other, because if it was greater than 10%, I'm going to be padding an awful lot with zeros, and I lose a lot of information when I have just zeros. A vertex of degree 0 basically means a point hanging off by itself, not connected to anybody else. So I don't want to have a lot of those things hanging off by themselves if I can avoid it. So you can have 2 graphs that have the same number of edges, vertices, and cycles, and then still have completely different degree vectors. This is part of one of the things that make graph isomorphism such a hard problem, is because you would think this is a small graph. It's a really small graph. You would think there's not too many ways to put it together. Well, no, there's 2 ways to do it right there, so these are non-isomorphic graphs, even though they seem very similar at the outset. So now once I have these 2 vectors, I'm going to use the Pearson coefficient as a distance measure. And the reason I chose Pearson is because Pearson will give me a number between -1 and 1. I have an actual range I can look at. So when I say it's 1, it's really close together, and it's very similar in their linear progression through their vectors. But if it's 0, it's not so much similar. In other words, it's definitely not similar. There's a lot of other methods. There's one that is, it uses the eigenvalue of the adjacency matrix of the graph called the graph spectrum. That doesn't really have a range for me to tell how close or far apart I am, because it doesn't just depend on the number I get out, it also depends on the size of the graph. So you have to combine 2 things to get some sort of idea, and quite frankly, I've been in computer science too long, I'm lazy. I just wanted a number that would say, okay, it's 1, great, I'm fine. Because I've looked at the spectrum of these things, and I've gotten out the number 5, and I'm like, what does 5 tell me? 5 whats? Or as opposed to if I look at 2 and I get the answer out of 0.95, hey, those are close together. Now here's another problem. Another problem is you can have 2 graphs that are distinctly different, but the Pearson coefficient of the degree vectors is 1. I like to say they sing the same song when they're moving through the vector. For example, we have two graphs. One has 42 edges, 10 vertices, and 33 cycles. The other has 29 edges, 10 vertices, and 20 cycles. So the same number of vertices, but they have completely different degree vectors when you look at them. However, the Pearson coefficient is 1 in this case. But I looked at this and said, you know what? I don't mind, because this is telling me very similar behavior between the two. This is the same pattern of behavior between the two. So yeah, they're slightly different numbers, but they're moving in the same way through the things. You have 1, 2, 3, 4, 5, 6 vertices that have a high degree, then 2, and you have the same movement through the next one. So I like that. I figured it was okay, and if someone else has a better way of doing graph similarity, I will be more than happy to look at it and possibly apply it. So now that I've digressed into graph theory, and I hope I didn't lose too many people or put anyone to sleep. No one seems to sleep much. The last step of the refinement is I say two graphs are in the same cluster if their Pearson coefficient is greater than 0.9. So now what I did is I took those clusters I made out of the LBNL data, and then I clustered the clusters. So when delta is 1, I get 99 clusters, which was cluster 756 graphs. So some graphs don't get clustered, which is something to look at, because you might have a whole bunch of things going to the same port on the other side, which is a bad guy. But you don't have anybody else modeling that sort of behavior. So all of these for delta equals 1, I just pulled a cluster out at random. Most of the stuff I chose at random. There was no actual thinking and looking for the best result. It was just closed and going, okay, I'll look at that one. All of these graphs had, that shouldn't be SIP, that should be S-port, and 50,122 in common. It can be used for SAP, Symantec, and SSH forwarding. I have no idea what they were doing, because I'm just looking at port. I'm not also looking at port and protocol or YAF. I'm just going, I looked at port, and this is what I got out. So without more information, I have no idea what's going on, which I think is pretty much true of all of us. Without more information, we have no idea what's going on. Another cluster had 50 graphs, and port 80 was common across the cluster, but there was no common node. So what that means to me is all the web traffic was very similar in nature with the encounter complexes. So the next thing I did is I said, okay, I looked at a single complex. That was fun. Now what if I have 2? What happens? So I chose a second time period from the LBNL data source. And I basically, seriously, I just looked and said, oh, that looks like a good time. I have 2 sensor imports from it. It'll work. And this time I got 14,676 components. For the record, components means independent subgraphs within the complex. I've been told that's not actually a term most people use. So then I compared these 2 complexes using the same criteria, and I left off of. And I found 63 clusters when I compared the 2 graphs, containing a total of 2,087 subgraphs. And I examined one with 8 subgraphs. 2 came from one, 6 from the other, and the common port was 427, but the destined IP varied. I have no idea what port 427 does. Isn't it location or something? So, future work in this. I need to weight the encounter complexes with the amount of bytes that are traveling across these packets, because I've paid absolutely no attention to those at this time. That actually really pays a lot when you're throwing the graph algorithms across. And protocol. Yes, I need to throw protocol in there along with port. The third fun thing I'm looking at is persistent homology. Persistent homology is a topological data analysis method that was actually used in encounter complexes devised from wireless traces to say, here's the structure of your wireless setup. Well, I can't really do that. I've never been able to figure out a way of deriving someone's network from the information I get out of Flow. However, I can use it to compare complexes. So one more thing before I move to questions and comments. I have been talking to quite a few people around here. I am starting a journal at CERT called the Journal of Digital Threats. It is looking for timely work, and we're looking for fast turnaround. And we're actually looking for people who are reviewers that actually do have an idea about the substance that we're looking at, of the new threats. You know, if I hand it to an academic journal and they say, where is your proof is a new threat, as opposed to I hand it to you and say, here's why it's a new threat, there's a different difference going on, not a distance. So if you have any questions or comments about it, please find me. I'd love to talk about it more. And any questions about what I actually just talked about?
You went over the beginning kind of fast, so I didn't quite catch what delta was and how that affects the graphs. you're
Delta is
generating.
time.
And so you're merging graphs based on delta?
Yes. So where delta is time, I'm like, I want the start of one to be within delta seconds of the end of the other. So
Okay.
if it's like 1 second, they were very close together, 50 seconds, they would be very apart. And you know, infinity means they were somewhere in the flow anywhere.
Okay.
How big do I think I can get these?
Now, how big can you go with that conversion?
What, infinity?
Oh, no, you said you were trying to approach complete problems very hard. You got it to go.
Oh, well, that's the graph isomorphism problem to tell if two graphs are exactly the same. So I'm looking at ways of saying how similar they are.
Graphs are cool.
Thank you.
And I think I do have an appreciation for what you've done here, and it does look like a cool derivation, but you did go very fast. I did have my coffee, but I still couldn't quite keep up.
Okay.
Is there a written report or a derivation of this
I
that we
do
could
have
get?
a written paper on the subject. If anyone gives me their cards and say I want the paper, I'll send it to you.
That would be terrific. Or maybe we could just sit around and talk about it for a long time. But I'm
I mean,
interested
I'll
in
give it, if
exactly
they
how
can
you build
download it
these
from the
graphs.
FloCon site, I'll put it up there, but I'll also send it out to anyone who wants it.
Okay, thank you.